All right, so are there any questions on the homework in 4.2?
Oh, yes.
Okay, let's go for it.
It's just one. The other ones I got it. But 22.
22, where it says given cosine of this number
Or decimal point.
of a decimal, find
Yeah.
sine and tangent. Okay, so the cool thing about ratios, actually the really cool thing about ratios, is if it doesn't give us a fraction, it gives us a decimal number. A decimal number, like let's say that one is, what, 0.0326? 0.0326. Is there something we can put underneath that, like divided by some number that doesn't change it, or is just kind of an assumed? We could put a 1 underneath that. So if we said this, is that number any different?
No.
No, we just divided by 1. I mean, you can multiply by 1, you can divide by 1, nothing has changed. So that means that if we said 0.0326, that is the number, yeah, 0.0326, that's the same as saying 0.0326 over 1. Now, if that's cosine, cosine of theta equals, and what was cosine of theta? SOHCAHTOA?
Adjacent and hypotenuse.
Adjacent and hypotenuse, and if we're writing that with x and y, so
This is x over r.
So this is the angle, the adjacent one is x, and the hypotenuse is always r. So that means your SOHCAHTOA, C-A-H, cosine is adjacent over hypotenuse, means x over r. So if that's x over r, that means that if our radius is 1, our x value is 0.0326. Oh man. Yeah, I'm going to try to draw that, but what's that going to look like? If our radius is 1, so let me just go ahead and stick our line on here. Okay, to get the x to be 0.0360, I mean that's not 0, but that's getting pretty close to 0, and the r is 1, what's that angle going to have to be? Really large or really small?
Really small.
Really small? Really small would be down here.
Large.
It's going to have to be really large because this is very small. Very small. So if that distance is very small, but our radius is still 1, the only way to make that happen is, erase the rest of this, and try to draw somewhat of a realistic triangle on here. This is like here maybe, with the radius being 1. It's still a 90 degree. Okay, and the angle, therefore, because the angle always starts from that x side. So, in fact, even that's probably not even enough of an angle. So, if we were to guesstimate what our angle is going to be with that, we could probably say pretty darn close to 90 degrees. Not quite, but it's going to be really close to a 90 degree angle. Well, what the question is asking here is find sine and tangent. So, sine of theta, tangent of theta. Sine equals y over r, tangent equals y over x. Okay, so we already know that we have a little bit of this, 1, and we know we have x, so 0.0326, but the y is missing. We don't have y for either one of those, so we can't do it at this point, but can we find y? Okay, just by looking at this, if you have a line that has a length of 1, and then a line right beside it that's almost exactly the same line, this line is going to be pretty close to what number? Pretty close to 1, right? I mean, if these two lines are almost the same number, this is going to be so close to 1 that our calculator might even actually try to round it as 1. But let's see, it'll be shy of 1, because we know we can't have a line longer than the hypotenuse, but it's going to be pretty close. So we can figure that out by saying y equals the square root of r squared minus x squared. Remember that one, just rearranging that Pythagorean theorem a little bit? And what do we end up with? Because 1 squared is still 1.
0.
Minus
999.
what?
0.999.
0.999 rounded. I'd say that's close to 1, but yeah, let's go ahead and keep the 999 there just to make sure we're keeping them straight. And that's our y value. So 0.999 0.999. So if the sine of theta is 0.999 over 1, what's any number over 1? It's just that number, right?
Yeah.
Itself. So 0.999. Now this one, okay, so this one isn't, it's an even number, so it isn't given in the back of the book. So we won't be able to match it and see whether they rounded it to 1 or not, but 0.999 is good enough. What about the other one? How do we figure out what that is? Because that's not over 1. But how do we figure out what that is?
Just divide the 2.
Just plug it into your calculator just like it shows up and hit equals. Now if the tangent, what the tangent means is a ratio of how big is this side compared to this side, or how many times bigger is this side than this side. I mean, just by looking at the triangle, I can tell this side is going to be hundreds of times bigger. Hundreds of times, maybe even thousands of times bigger. I don't know exactly what the number is going to come out to, but that tangent is a ratio of how big is this compared to this, many times bigger. Many times. So what does tangent of theta come out to when you plug it in?
30.592.
What?
0.592.
0.59? No.
30.4.
30.6? Okay, so it wasn't hundreds of thousands of times bigger. I guess my estimating was a little off. But I knew it was going to be a big number. So what is that?
30.64.
30.64? So that means that this side is exactly 30.64 times bigger than this side. That's what the tangent means. Since it's a ratio of one side to the other, for this given angle, which is pretty close to 90 degrees, this side is many times, 30 times bigger than this side. So as that angle gets closer and closer and closer to exactly 90, this side is going to start getting many times bigger, which means the tangent value is going to start getting higher and higher and higher the closer you get to exactly 90 degrees. Which that kind of stuff is what we're going to be going into in the next section, but are there any other questions on that problem set? My homework? Nope. All right. Okay, so 4.3 is the next section. And we're looking at what are the values of these trigonometric functions, and here's where we actually start putting the degrees into it. So far we've just been saying, as long as the degree is the same, then we're going to get the same values and the same ratios out. But let's start actually relating these to the degrees and see how that works in real life. So because I like 3, 4, 5 triangles, because the numbers are small and very easy and I can remember them, we're going to keep that one. So a 3, 4, 5 triangle, and for now we'll be able to derive angles, but for now I'll just let you know that the angle in a 3, 4, 5 triangle is 36.87 degrees. Approximately. It actually has a lot more decimal places than that, but it's good enough to say 36.87 degrees. Three, 4, 5. So 3, 4, 5 triangle. Now we already determined that we could get the sine, cosine, tangent values, and all the other 3 as well, based off of 3, 4, 5, because we're just sticking in the numbers of the sides. So what is sine? Sine of theta is SOHCAHTOA, sine opposite over hypotenuse, 3 over 5. And what does that simplify to? 3/5.
0.6, right?
0.6, yep. 0.6. Another reason why I like the 3, 4, 5 triangle, because the decimal numbers that match them come out to nice even numbers. A lot of times when it's like if you're working with nice even degrees, nice even angles, the numbers don't come out very even, But if you're working with nice even numbers, the angles don't come out right. It seems like there's not really any good combinations that give you this nice perfect world. But that's okay. We don't need to worry about that because we'll see that all of them relate to each other. So if the sine of this angle is 3/5 and this angle was 36.87 degrees, should equal 0.6. If we plug into the calculator, we should hope to see that. So go ahead and plug that in, and I'm hoping everybody's going to get 0.6, but you might not. You might get some number that's like a negative something. Hopefully everybody gets that. And there is a reason for that.
Yeah.
0.51.
What?
0.51. I got 0.6.
0.6, 0.6, 0.6, but just type it in wrong. But no, that's okay. If your calculator does give you something different, that might not be a bad thing. That's totally okay. But the difference is there's different forms of angle measurements. Degrees and radians are the two most popular ones. There's also gradians, graduated radians. We aren't going to be dealing with those, but radians are an angle measurement. They're just a completely different scale, but we can still plug them into the calculator, and the calculator is not going to know any different if we just say, hey, give me the sine of this angle in radians, and you type in the degrees. Well, how's it supposed to know you're typing in degrees? It thinks you're typing in radians. So here we're going to go ahead and take a little bit of a pause and make sure all the calculators are in the right mode, or at least that you know how to switch them. So there's Casio, TI Scientific, TI Graphing, and Sharp calculators. Does anybody have anything other than one of those? Okay, cool. Because that means I made sure to get the order of operations for getting those in the right mode. If you have any others that seem to not have any of these, let me know afterwards. And every calculator seems to have slightly different buttons that you have to press, and it's no big deal. It's just sometimes it can be kind of frustrating when, well, here's 4 operations, and your calculator is not quite exactly the same as the other ones. But as long as we all at least have similar types of calculators, we're good. So the Casio one, there's a mode/setup button. So going into that one, there's the setup is usually the second function of the mode. So if you go into that one, Casio, and I don't know if this is the same for Casio graphing calculators, but hopefully nobody has one of those, so it's not that big of a deal. Setup, and then you can press the number 3, which says DEG. There's degrees. For the TI Scientific, like the TI-30, TI-30X, things like that, TI Scientific, I'll just call it TI-SCI. There's a button, DRG, that's that acronym, degrees, rads, grads. So DRG, when you press that button, it's going to give you 3 underlined options. You can either have it in degree, radian, or the DRG mode. So, and it'll be GRAD. So we want to select DEG with the underline. So go navigate with the arrow keys until it's underlined, hit enter. And it probably is already in there if everybody got the same number. TI graphing. They have a lot more pixels here, so they can afford to actually give you a full word. They don't have to abbreviate to DRG. They can actually give you the entire word degree. So mode. Degrees. You either have degrees or radians. Those are the 2 most popular ones. So if you have a TI Scientific mode, and then either degrees or radians. And then the Sharp calculators, like the Sharp EL, the scientific ones. Again, there are probably going to be some in here that don't have exactly the same order of button pushing, but we'll get it figured out. So the setup, kind of the same as the Casio one, because they're very similar types of calculators in their orientation of things. They also have a DRG. Same thing, degrees, rads, grads. Find the degrees, underline, hit enter. So not only is, it sounds like pretty much everybody's was already in degree mode, which is good, but later on we're going to be getting into radian mode too, so it's probably good to be at least somewhat familiar with, okay, just hit and we're in radian mode. And then hit it again, we're in degree mode. And it's really easy to flip-flop back and forth. But if you look at the top of your calculator, they'll usually have a DRG, so one of those will be highlighted to let you know which mode you're in. Sometimes it'll say DEG or RAD, or a real quick check is plug in sine 36.87, close the parentheses and hit equals, and you should get 0.6, or a number very, very close to it. It's like 0.60000, and then a couple other numbers, but that's because this is slightly rounded. So do that check, and if you can't see the DRG or degrees somewhere on it, just type in this, and if you get 0.6, you're in degree mode. So we're ready to move forward. Okay, so clear this off and give us a little bit more space back. So, as a trig ratio, what that means is the ratio of the opposite side to the hypotenuse is 0.6. Just like when we were looking at tangent was the ratio of the two sides. You know, one was how many times bigger than the other. This one is 3/5, which means the opposite side to the hypotenuse. It means this one is exactly 0.6 times as big as this one. That's what a sine is always going to mean. This one is that many times bigger than this one. Well, obviously, if the number is less than 1, it means it's smaller, right? Can this number ever be bigger than this number? No, because then it's not a triangle anymore. We can't have one of the sides bigger than the hypotenuse. So is sine ever going to be bigger than 1? No. It means, if that was possible, it would mean this is going to have to be bigger than this. It's not possible. That's not a triangle anymore. So that means that in sine, no matter what we try and plug in for sine, we're never going to get a number bigger than 1. They call it a domain, which means, or a range, a set of outputs that it will be able to give us. And no matter what we try and plug in, no matter what we try and fool it with, or try and put it in radian mode and try to plug in something that's going to confuse it, we're never going to be able to get anything bigger than 1. There's no way. Now, we can get to 1, which we can get all the way up to perfect 90 degrees, which means this, that triangle, has now perfectly matched the same as the radius. We got no movement side to side, it's all vertical, which means that now those two lines are the same. Well, now technically that's not a triangle, but we do have that point when the radius is moving around in its circle. We do have a point where it hits 90 degrees, and for a split second right there, they're both straight lines that are the same radius. So that means that if we plug in sine of 90, what should we expect to get? What would be the ratio between this? We call that a 1-to-1 ratio, if they're both the same number. It's 1, right? Sine of 90 is 1. And likewise, if we went all the way back down, straight line horizontal, that would mean that this 3 is getting smaller and smaller and smaller and smaller and smaller until finally it's 0, right? And when it's a straight horizontal line, it's all in the x direction, nothing in the y. So if we put this in, we'd say, well, our radius was 5, but now our height is now 0 at the angle 0. So what would we expect to get if we plugged in sine of 0?
0.
A 0. Sure enough, what do we get? Sine of 0 is 0. That calculator confirms that?
Yeah.
Okay. So that means that we can already identify a little bit about these ratios just by kind of seeing how they fit into this triangle, this right triangle notation. Now again, we cannot determine anything about these, or at least without a little bit more difficulty, if this is not a right triangle. So that's why basically this whole class is about right triangle trigonometry. We're assuming, even if I don't write the angle, that little square thing in there, we are assuming that everything in here is going to be 90-degree angles, unless specifically told otherwise, which can happen. Sometimes you have to find those different angles and try splitting them into a 90-degree angle in order to see how to solve that using the trig functions. But as far as all these examples, it's only going to be the actual 90-degree angles. So we did get 0.6 on this one, right? 0.60001 or something.
Yeah.
Okay, I did abbreviate this one because when we get to this point, we actually try to calculate that. It's actually 36.869 going off into a lot of decimal places. So it's not going to be exactly 0.6, but it's close enough for what we're caring about. Just enough to verify that, sure enough, whether we do it by hand, by looking at the numbers, or by plugging into the calculator, we get the same ratio. That's really what I'm driving at here, is that these aren't strange notation things. It's just a label given to a ratio of two sides. So this side to this side, there's going to be a certain scaled difference between the two of them. But they all make perfect sense. Like these ones already, we were just able to look at some stuff and determine what's sine going to do at certain angles. What is it going to be? So, along with that, let's look at cosine and tangent, try to identify some of the same properties of those. I'll just take out this one, leave that. Cosine, what is cosine?
X over R.
X over R, which is the adjacent side. All right, so katoa, C-A-H.
Opposite over adjacent.
No, so katoa. So cosine is the
adjacent.
which you were right. So X, because that's the adjacent side. X, which is 4 over 5, equals 0.8. Plug it into the calculator. Cosine of that number, 36.87. We get the same thing. It's like 0.8 or 0.79999. Is that what we got? Points.
999.
Yeah. So as close enough as we need to call that 0.8. How many decimal places do we want to start going off the screen before we can just say, yep, that's 0.8. Sure enough, that's what we get. So cosine of that angle is 0.8. Now, let's look at the same kind of thing. If we started increasing and decreasing that angle, let's see if we can determine what's going to happen at cosine of 0 and cosine of 90. So if cosine refers to the x, as we start decreasing that angle, what happens when it's perfectly horizontal? Do we have any up and down motion?
No.
So that means it's all horizontal, all in the x direction, which means the radius and the x will have a one-to-one relationship. They'll have a one-to-one ratio with each other. So cosine of 0 degrees says that for every distance we go out in the radius, that's the same distance the x is going to go out. A one-to-one ratio, which 1 divided by 1 simplifies to 1. So if we plugged in cosine of 0, what would we get? 0? 1. So think about this. Once we get down to 0 degrees, if our radius has been moving around in a circle and it gets right there, I mean, yeah, again, this is that case where technically we don't have a triangle, but that radius can hit 0 degrees and 90 degrees and 180 and 270. So we should be able to at least get something here. And if the radius was 5 from here to here, x equals? No, x doesn't equal 1. Right, as we're moving that radius down, if that radius is 5, right at this split second, that's 5 units out. So if this radius is 5 and the x distance is 5, what ratio or what relation do those have to each other?
1.
It's a one-to-one ratio once it's simplified. That means cosine of 0, cosine of 0 without the little line through it, cosine of 0 should equal 1, and what do we get? 1. And when you plug in your calculator, cosine of 0, that's what you get, is 1. So sine of 0 was 0. Cosine of 0 is 1 because it's dealing with the horizontal distance instead of the vertical distance, which means those were exact opposites of each other. Well, could we kind of predict the same thing with a 90-degree angle? Maybe. So if our radius was starting to swing up, so we took that endpoint and just pulled it straight up. Radius is still 5. So R equals 5, and we're straight up at a 90-degree angle. How much of that is horizontal? How much of that is going in the horizontal direction? 0. So that means that x over r, which is cosine, our x is 0. We have no horizontal side-to-side motion. 0 over r, doesn't matter how big r is. 0 divided by anything is 0. So cosine of 90, so cosine of 0 equals 1, because it was a 1-to-1 ratio. Cosine of perfect 90 degree, don't care what the radius is, does not matter. We don't have any horizontal travel, which means cosine of 90 is what? 0. Again, we've determined a little bit of similarity here. So let's look at one other interesting angle. What's between 90 and 0 degrees that is kind of a interesting angle to look at? 45s? Certainly there's 90 degrees in between, so any one of them is interesting, but the 45-degree angle is kind of interesting, particularly in terms of sines and cosines, because of an interesting property that they both have. So if this is 45 degrees, we'll ignore that for now. So if that's 45 degrees, why cross it out? It's a whiteboard. Then this side is also 4 units. Right? 45 degrees means that both of the legs of that right triangle are the same. Now we could use Pythagorean theorem to figure out what that third side is. But do we also have a little bit of an ability to see what's going to happen with our sine and our cosine values? So sine and cosine. Sine is which one again? Opposite over hypotenuse, which is 4 over whatever our r is going to be. What about cosine? It's the adjacent side, right?
So 4 over r again.
Well, interesting. Now, is the r going to be the same between them? Well, I sure hope it is, because it's the same triangle, so the radius is going to be the same. Well, what's interesting about those?
Exactly the same.
They're going to be the same. So let's try plugging in cosine of 45 degrees and sine of 45 degrees.
Both 0.7071.
0.7071. Or 0.707.
Yeah.
Okay, yeah, you guys know that. But what does 0.707 mean to us?
It's 0.7071.
Okay, well, yeah, that's what it means. This number, 10 equals 10. Yeah, that's
Magic number.
mind-blowing. But what is...
RMS.
Okay, yeah. RMS. Yeah, okay, we got it. But in terms of this, a sine and a cosine value, what does sine mean? Ignoring this number, going back again to what does sine mean? It's a ratio of what? It's a ratio of this side to this side, right? So our calculator just told us that for a 45-degree angle, no matter how big these two get, the ratio of this one to this one is 0.707, which means this one is 0.707 times smaller than this one. This one, therefore, has to be that much bigger. Or if you want to go inverse, you divide by 0.707 instead of multiplying by 0.707. So if we know that this side is 4, then this must be 4 divided by 0.707, because we know it has to be bigger, so we can either multiply by 0.7 or divide by 0.7. Well, one is going to be smaller and one's going to be bigger. I hope nobody would put a smaller number here. You know, look at 4 and 4 and say, oh, that must be 2. No, that's not possible. So, of the two options, 4 divided by 0.707, what does that equal?
5.65.
5.65-ish. And yeah, there was some rounding going on. 5.65. Is there another way to figure that out?
Yes.
Yes. He says yes. What is it? The Pythagorean theorem. What happens if we do 4 squared plus 4 squared, or 16 plus 16, and then take the square root, or square root of 32? Same answer? Well, that's good. I would hope that it's the same answer. You know, and we're going to maybe have a couple like decimal places out here. You know, it might be 5.64 instead, but some of this in trig, that's the whole point. We have to kind of determine where are we going to cut the decimal places off and say, okay, plus or minus 0.01 or 0.02, close enough. But we can see that if we use Pythagorean theorem, or just by knowing the definition of what sine and cosine mean, we actually don't even need the Pythagorean theorem here as long as we've got the other two sides. And we can figure out any of those three sides no matter which one's missing, because conveniently they've given us 6 different combinations of sides, sine, cosine, and tangent. So whichever two they gave us, we don't necessarily have to worry about all the square rooting and squaring and all those kind of things. Although really it's not that hard, but it's just to show that there are very easy ways to look at two sides of a triangle instead of having to figure out all these other things about it to fit them into some other property. We can just use one little helpful key and figure out what this is going to be. In fact, in this case, it's just two numbers divided by each other. Okay. Let's see. I want to make sure in this case that we've got it all conveniently set up for being able to easily do all the homework. Exercises 9 through 24 in this set, you'll actually probably find those extremely easy because it says find the value of the trig function. What's the easiest way to find the value of a trig function if you know the angle? Just put it in equals. Okay, but we could also maybe do a little bit of estimating or guesstimating what this is going to look like. So we'll draw a little bit of a sample angle here. Horizontal and vertical sides. So let's look at sine. So we'll look at some different possibilities of what is the sine value going to be as we move around this angle. And in all of these, they've limited it to the 0 to 90 degree range. We really have 360 degrees of this, so we actually have a lot of options that we'll be looking at because, you know, full circle, it can go all the way around to 360 degrees. So obviously, sine and cosine are going to have to mean something at that point. But for here, they're just saying, let's, at this point, just examine the 0 to 90 degree range. So we draw a circle and call this our R. Our radius is the distance out to there. Let's look at sine and try to pick those points. So sine of the angle, we already determined what it was at these 3 points. So at 0 degrees, 45 degrees, 90 degrees. Okay, what was the sine at 45 degrees? 0.707. Okay, what was the sine at 0? Since sine is height.
0.
What's the height when we've got a flat line? 0. And what's the sine of 90?
1.
1, because it's all height at that point. So knowing this, 0, 0.707, and 1, we can actually kind of start guesstimating a little bit what our numbers are going to fall within, like the first angle, or that first problem. Problem 9 says sine of 22.4 degrees. This was 45, 22.4 degrees. It's right about in here. Okay, now an interesting thing about curves is you would think if we have 1 and 0, halfway, which is 45, should be 0.5, right? Halfway between 0 and 1. This is a sweeping angle. It's a circle radius, so it actually doesn't work in just like a line where you just cut it in half. But it at least gives us a little bit of getting some of those points narrowed down. if it were a perfect angle, if we graphed sine and cosine, if this were a perfect split, we'd see a straight line up, straight line down, straight line up, straight line down. But that doesn't happen. It actually curves up, the sinusoidal curve. It curves up and down, which means it doesn't have a perfect linear relationship of exactly cut it in half, cut it in half, cut it in half, like that. But it doesn't mean that we can't at least have some idea what we're going to get out of it. Do we know that if it's at 22.5 degrees, or 22.4 is it?
Yes.
Yeah, 22.4 degrees. We know that it's going to be less than 0.707. Trace our line straight down. And the sine is going to say, what's the ratio of this side, the height, to this side? So if we just assumed that to be a 1, let's call the radius 1. Doesn't matter. That's the nice thing about ratios, is they don't determine the absolute size of the triangle. They just determine the ratio of this side. For every amount this side increases, this other side, one of those other two sides, is going to increase by the same amount. We don't know exactly what the absolute size is, but sine and cosines aren't concerned with that. So we call this with a radius of 1. And some handy things start happening because we can just put a 1 in there. 4 over 1. I really like dividing things by 1. It makes math a lot easier. It's almost as nice as multiplying by 0. Which, yeah, we'll multiply by 0 a few times. But hey, dividing by 1 is one step shy of that. So our radius being 1, and that's a term that they call the unit circle. It means that 1 is the unit. 1 unit, 1 foot, 1 meter, 1 inch, 1 mile is the distance from the center to the outside of that circle. 1 unit. Therefore, all we have to do is just figure out what is the ratio of how big is this going to be versus 1. So that means our sine of 22.4 degrees equals some number over 1. Now, if we've called that 1, the calculator is just going to give us a decimal number. It's just going to say, it's going to be obviously less than 0.707, but more than 0. So we're down in the lower range of that. And what does that end up giving us?
0.381.
0.381, so roughly 0.381 if the radius is 1. Sure enough, that's okay because it wasn't more than 1. If it was more than 1, then we'd start getting a little worried because now our sine value, that means our height is more than our radius, and that's impossible. So as long as we get a number less than 1 and it fits our logic test of 0.707 to 0, and this seems drawn somewhat to scale, seems to be about halfway there. So makes a reasonable guesstimate. And then 0.381 is exactly what the calculator says. So after we at least have an idea of what we're doing here, then we can plug into the calculator and verify that we're getting the value that we should be. 0.381, which means now if we wanted to solve for the cosine value, that third leg from here to here, 0.381, how hard is it at this point? Or what tricks do we have? What two methods do we have now? If we have two sides of a right triangle, what's the equation that relates all three of the sides together? We could square both sides, subtract them, then take the square root of that. Do we have a ratio of this side to this side? SOHCAHTOA. Which one is the adjacent? X is the adjacent. Sine was opposite over hypotenuse, so cosine is adjacent over hypotenuse. Cosine of 22.4 degrees equals adjacent, or x over 1. That's going to give us our x value. So yeah, we could do the square them both, then subtract, then take the square root of that. Or we could say cosine 22.4. And what does it give us?
0.924.
0.924. Does that fit somewhat to scale drawing? 0.924. Okay, what is this distance from here to here? That's 1, right? Because the radius, once it gets all the way down to 0 degrees, that is the radius. So drawing this, and looks like it came out somewhat to scale, pretty close. This amount at 22.4 degrees is getting really close to that end point, to those matching, to them being a 1-to-1 ratio. Not quite to a 1-to-1 ratio yet, but we're at a 0.924 to 1 ratio. So if this was 10 miles, this would be 9.24 miles. If it was 100 miles, this would be 92.4 miles. So it's always a 0.924 to 1 ratio. And then the tangent, the only one that we haven't covered, and probably the only one that we'll have time to cover here. Final one. Tangent opposite over adjacent, SOHCAHTOA, tangent equals opposite over adjacent. And in these examples, using our x and y, which one is the opposite?
Y over X.
Y over x. So y over x. Okay, first of all, let's look at our 45-degree angle here. Can you already tell me what the ratio of this to this is with a 45-degree angle? It's a 1-to-1 ratio, right? Does it matter how long those sides are? If this was 8, how long would this be?
8.
If this was 1,000,
1,000.
1,000. It's a 1-to-1 ratio. So if our tangent of 45 degrees, we've got that button on the calculator too. Tangent of 45 degrees equals? 1. That's what we got, sure enough?
Yep.
Tangent of 45 equals 1. That's a 1-to-1 ratio. Now when the calculator gives us an answer, it's always going to give us a decimal answer. I think you can set up some calculators to give you the exact value, which is a fraction, but usually not. It's going to give you a decimal number. Whenever you see a decimal number and you're thinking, how does that relate to a ratio? Draw a line and write a 1 underneath it. And that will be your reminder that, oh yeah, it's that to 1 ratio. 1 to 1. That means the x to the y, the ratio is 1-to-1 all the time. Doesn't matter how big it is, it's the same size, 1-to-1 ratio. What about tangent as we start getting down here? It's y divided by x. So what's happening to this side? It's getting smaller, and this is getting larger. So as the top of the fraction starts getting smaller and the bottom starts getting larger, what does tangent start doing? And here let's try an extreme example where this is like 0.01 and this is 0.99, for instance. What does tangent start doing? What does it start getting close to? 1? Plug in tangent of 0. Tell me what you get.
0.
0? Okay, so that's our, that doesn't quite work quite as easily on the other end of the spectrum, but if we're starting to get a really tiny number here and a number that's much bigger than that, and again, it's that ratio of y to x, we start saying that x is getting many, 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 many times bigger. Many times bigger, which the bigger numbers on the bottom of a fraction always makes the fraction get smaller. So the smaller we start getting, the closer tangent starts getting to 0. So tangent of 0 degrees equals 0. But anything shy of that, it's going to be getting close to 0. But now 90, oof, that one's a little bit more annoying. Try plugging in tangent of 90. What'd you get?
Error too.
An error? Oh no.
Domain error.
A domain error. Okay, so some say domain error, some say error, some say I can't do this. Why? Why can we not do that? What happens when we start getting right here? It's a ratio of this side to this side. So y over x. At this point, y is, what's the height right here?
Like 1.
1.
Because it's
What's the
dividing
x?
by 0.
How far are we going horizontally?
0.
We're not, which is the number 0, right? Well, that in math says domain error. We cannot do this. We can't divide by 0. It's like having one thing and then splitting it up into 0 groups. How many are in each group?
0.
You got 0, and then you literally have infinite leftovers because it's an infinite. You have infinite times more than 0 left over, but you can't split it up into groups. So you can't get divided by 0. However, I think on TIs, and Jesse, if you want to plug that in on yours, sometimes it'll give you infinity. I think only the TI-89 does that, but error? Okay. The TI-89 on some of them, it interprets it getting huge. It starts saying, well, this gets so many times bigger. I mean, if we looked at an angle that was 89.9999999 degrees, our tangent would start getting massive because that's when I was saying that hundreds or thousands of times bigger. If we plug in, the closer we get to 90, the bigger that tangent starts getting. So literally it starts growing to infinity when it gets extremely close to 90, but it can't actually get there because it cannot have a 0 on the bottom. It can have them very close to 0. 0.9999999 over 0.000000001 starts getting to be a big number, but as soon as we reach 0, it can't have it. So that means our tangent is fine all the way up to 90. We just cannot do it for 90 degrees. We also wouldn't be able to do it all the way around the horn down into 270. We wouldn't be able to do it there either. Okay, so at this point, go ahead and get started on 9 through 24. Problem set 9 through 24 on 4-3. So set 4-3. 9 through 24.
Mr. Peterson, we got 9 through 44.
Yeah. Go ahead and go ahead and do them up to 44, because really all that I've talked about today is just the ones going down to 24. But I think we've gotten enough of a good start to be able to at least get through 40. So if the other ones, if those don't quite work out, we do have until Friday when this is due. So I will be covering a little bit more of this on Wednesday. But yeah, go ahead and get started on all the way through 44. Actually, that'll probably be better that way, because then if you do run into things that they either make sense, we can just fly right through it, or if it doesn't make sense, then we can emphasize it a little bit more. Yeah.
So like 9 through 24, if you got like secant, would it just be the inverse of that?
Yes, in most calculators you can go into a second function or into a trig menu and find the cosecant.
1 divided by that?
But 1 divided by, yeah.
1 divided by,
yes. So if you found, if it said find cosecant of 20 degrees, find the sine of 20 degrees, 1 divided by that.
1 divided by sine of 20.
Yeah. Exactly. That's another thing I'll be going over on Wednesday too.